Okay, let's move on with our subchapter about macroporous materials. We have determined in the last class that we talk about macroporous materials when the pore size is larger than 50 nanometers. And we've also seen that we can make macroporous materials from the arrangement of spheres that have diameters in the order of tens to hundreds of nanometers into close-packed structures. Because, well, when we have a close-packed structure, then we have still 26% void space. And if the spheres are just large enough, then the voids in between are macropores. But we can also actually use the nanocasting technique in order to invert these packings of spheres into the inverted structure. Then we have also discussed how we can actually make these spherical particles. So we discussed perhaps for both silica particles, and we have discussed the Stöber process in this respect, and also emulsion polymerization in order to produce styrene spheres. And in the very last part of the lecture, we discussed techniques, how we can arrange these spheres into well-ordered close-packed structures. So now in this class, I would like to talk more about the properties of these close-packed structures. When we have well-ordered close-packed structure of these spherical particles, then we have what is called photonic crystals. So these photonic crystals can be artificially made, but they even occur in nature. For example, opals are photonic crystals of silica spheres that are arranged in a highly periodic close-packed structure. So if you take a scanning electron microscopy image of an opal, then you will actually see, as shown here, that the opal is being made of spheres that are arranged in a highly ordered, close-packed structure. So butterfly wings are another kind of photonic crystal made of a macroporous material. So in a butterfly wing, we actually do not have actual pigments, but we have proteins that are folded into a periodic macroporous array. Okay, so you see here an SEM image of a butterfly wing, and you see clearly that this is a porous structure, and the pores are in the macropore size range. So how do these photonic effects come into play? So this is essentially a diffraction phenomenon. Okay, so we have discussed diffraction already when we looked at the diffraction of X-rays at crystals. Okay, and similarly to that phenomenon, we can diffract visible light at structures that have approximately the same wavelength than visible light. Okay, so visible light has wavelengths in the order of 400 to 700 nanometers. Therefore, it gets diffracted at periodic structures that have lattice constants approximately the same range, and macropore structures fall into that category. Okay, well, when we diffract X-rays, then X-rays have wavelengths in the picometer range. Okay, and that's basically the same length scale as the lattice constants of regular crystals, okay, with periodic order at the atomic scale, okay. So the photonic crystals themselves are a large field, and we will touch that field only extremely briefly. If you're more interested into that field, I can actually recommend you here this online book that can be found on the MIT website. Okay, so let's look at this diffraction phenomenon more closely. Okay, so we have learned that in the case of Bragg diffraction, we have lattice planes, okay, and then the incoming electromagnetic radiation, in this case X-rays, get reflected at these crystal planes. Okay, and of course there is a reflection condition associated with this, which is the Bragg law. Okay, so for that reason, only under certain angles actually can we observe a diffracted or a reflected X-ray, which has a particular wavelength. Okay, so when we diffract visible light at a periodic macroporous structure, then we have a similar effect. Okay, so our light ray gets reflected at the periodic lattice. Okay, but in addition to just reflection, we now also have to consider refraction. Okay, because in the visible range, in addition to the diffraction phenomena, we also have the refraction phenomena to consider. And the refraction now depends on the refraction index on the material. And that refraction index determines by which angle the incoming light ray is actually bent as it enters the material. Okay? So therefore, the interference phenomenon that results from the interaction of the visible light with the macroporous lattice depends both on the incident angle of the light, but also on the refractive index, okay, of the photonic crystal. Okay, and therefore, in order to determine the reflection condition, we have to consider both the incident angle as well as the refractive index. And that is described in what is called the Bragg-Snell law, which is nothing else but a combination of the Bragg law with the Snell law for refraction. Remember, Snell's law for refraction is that n1 times sinus theta is n2 times sinus rho, okay, whereby rho is this angle here. So you see that the refraction depends on the refraction indices of the two media involved. Okay, so N1 can be, for example, the refractive index of air, and N2 can be the refraction index of your actual medium. Okay, so now we can combine these two laws to the Bragg-Snell law defining then the refraction condition for your photonic crystal. Okay, so we have m times lambda, n is just again an integer number, is equal to 2 times d, whereby d is nothing else but the interplanar distance within the photonic crystal times the square root of the so-called effective refractive index square minus the sinus square theta. Okay, only if this condition is being fulfilled, then we will actually see light. Okay, so this is the reason why opalescence is angle dependent. And we've probably all seen an opal, and you have probably observed that the color that opal has, okay, depends on the angle from which you look at it. Okay, and that is because the reflection condition depends on the angle under which you actually observe the visible light. Okay, so this is actually schematically shown here. Okay, so here you have the transmission as the function of the wavelength under different tilting angles, and you see that under different angles different angles theta, okay, you will observe wavelengths of different light. Okay, at 0-degree angles, you will observe the light with the largest wavelength, and the more you actually increase the angle, the smaller this wavelength actually will shift to smaller wavelengths. You see this in a different form here. Okay. So here at 0-degree rotating angle, we observe, a wavelength of approximately, 700 nanometers. So we are in the orange-red region, okay? But as we tilt, okay, then we go to wavelengths of approximately 500-degree angles, which is in the bluish green region. Okay, so there's one term we have not discussed thus far, and that is the effective refraction index. So the effective refraction index is nothing else but, or is related to the sum of the refraction indices of the two media weighted by their volume fraction through the Lorentz relation, which is mathematically given here. So we have to consider that our macroporous material is actually itself composed of two media. So for instance, when we have a photonic crystal made of silica spheres, then we have to consider the refractive index of the silica spheres themselves, but also the refractive index of the material in between. That can be, in the most simple case, be air. Okay, and the effective refractive index is then related to the sum of these refractive indices weighed by the volume fraction of silica versus air, respectively. Okay, so not necessarily you have to have a porous material in order to have a photonic crystal. It's actually sufficient when you have periodic order at the macroscopic scale, when there is actually a significant refractive index difference between the two phases. Okay, So, for instance, you can also make photonic crystals from block copolymers. Okay, and in this case, the block copolymers have block sizes which are 50 nanometers or larger. Okay, and then these block copolymers, blocks of the block copolymers segregate into paired ordered arrays. Okay, whereby the exact phase that forms depends on the relative volume fraction of the um, volume blocks. So you see that when we have 0.0 to 13% volume fraction of the minority phase polymer, then we are getting spherical entities that are being packed into a closed packed structure. In this case here, it's actually a body-centered closed packed structure. When we have a volume fraction of 13 to 33%, then we are actually getting cylindrical aggregates that are well separated by the second block. If we further increase that volume fraction to 33 to 37%, then we can get gyroid structures, or what is called a double diamond structure. So this is basically a diamond network, which is actually double interpenetrated. So one diamond network is interpenetrated by a second one. And if we go to 37 to 50%, then, well, the tendency for curvature of the minority phase is completely eliminated, and we are getting actually lamellar structure. Also, lamellar structure can be photonic crystals. All right. So there are a number of interesting applications for photonic crystals, and I touch this only here very briefly. So one company, it's called Opalux, actually pursues these two applications here. So they have developed what is called a P-ink and an elast-ink. Okay, and that so-called P-ink can actually produce voltage tunable full color opal coatings. Okay, so in this case you have silica spheres, okay, that are arranged in a periodic structure, embedded or surrounded by a matrix of a redox active polyferrosenylsilane gel. Okay, so one phase in this case is silica, and the other phase, okay, in between the silica spheres is the polyferrosenylsilane. So that second phase is redox active. Okay, so you can oxidize and reduce the iron in that polymer surrounding these spheres. And as you oxidize the iron from iron 2 to iron 3, that polymer swells because it needs to accommodate additional counter anions. Okay, so as the polymer swells, okay, the silica spheres are actually further apart, and that changes the lattice constant of your photonic structure. And the change in the lattice constant then changes the color of the material when observed under a specific angle. Okay, And if you can just basically change the lattice constant of your material wide enough through the application of a voltage to that redox active material, then you can actually tune the color of the respective material over the entire visible range. Okay, so you only need one material, okay, but then just by adjusting the voltage to it, you can tune the color from red to green to from blue to green to red. Okay, so this is something which is not possible with any other, well, optical material. We cannot tune its color over the entire visible spectrum. So here's the other application. So this is called elast ink. So in this case, we change the lattice constant of our photonic crystal through mechanical pressure. Okay, so this is illustrated here. So here we have our photonic crystal. Okay, so we shine light on that photonic crystal, and then because of the Bragg-Snell law, selectively one wavelength is being reflected, and that is the wavelength that we can observe, determining the color of the material. Okay, but the exact wavelength, of course, depends on the lattice constant of your periodic structure. So when you actually press on your material, okay, then you deform your material, and the lattice constant is actually changing. Okay, and then the reflection condition is fulfilled for different wavelengths. Okay, and you will see a different color for the material. So this can be, for instance, been used for counterfeiting techniques. You can actually embed, meanwhile, photonic crystals into banknotes, okay, which is technically very difficult. And when you actually press with your finger on the banknote in a particular area, and the banknote then basically changes its color in that area, then you know it's actually the real banknote and not some counterfeiting product. Okay. You can also use this principle for identification purposes. So when you can actually use it for fingerprinting, okay, because your surface of your finger is not entirely flat. So when you actually press with your finger on your photonic crystals, then a different pressure will be applied to different areas of your photonic crystal, which you can actually then visually see. So this technology has also applications in identification. All right. So this is what I wanted to tell you about photonic crystals. So let us now move over to the next chapter. We will continue with porous materials. Which will be about metal organic frameworks and covalent organic frameworks. Okay. These are also porous materials, but they are not macroporous. They can be either microporous or mesoporous. So we are taking a step back in pore size again. So to say, So the first porous metal organic frameworks were discovered in the early 90s, and the principle behind metal organic frameworks is to interlink simple metal ions, for example, zinc, with rigid organic anions, whereby these rigid organic anions then act as spacers in between the zinc ions, producing porous frameworks. Okay, so this concept has inherent great variability because there are so many organic linkers that you can think of, which are just anionic and rigid, and so many different uh, metal cations that exist throughout the periodic table. So the probably most famous metal organic framework is the MOF5. Where's my the pointer? The MOF5, which is nothing else but a salt between zinc 2 plus and this para phenylene carboxylate anion here. And you see an exert of the overall structure here. So you see here these blue tetrahedra, and in the center of the blue tetrahedra, there is the zinc ion. Okay, so you have overall 4 zinc ions here, and these zinc ions are coordinated by oxygen. Okay, so one oxygen is actually an oxide anion, an O2 minus anion. Okay, and this one sits actually here at the center. You can see it here more clearly. Okay, this is nothing else but an O2 minus, which does not belong to a carboxylate linker. And then the remaining corners of these tetrahedra contain oxygens that belong to these carboxylate units. Okay, you see this here and here, and here, and here. And then these organic linkers interconnect these tetramers of 4 tetrahedra. And that overall gives you a cubic structure, as you can see. So you can see overall here 1 pore that results out of that kind of connectivity, but the overall framework extends, of course, over many repeating units. So this can also be seen 3-dimensionally better, and I have actually prepared that for you. Now I just need to find it here. Yeah, I don't know how to find the website now here. Wait a sec, please. So I have to find the browser now, because that's the internet. So I don't know why I can't get out of this. Oh yeah, here we are. So we have this, and that we have to share now. Yeah, so this is this. Let's share this. And you see here actually on the website ChemTube 3D, which I mentioned to you previously already, the MOF5 structure. And you see now here actually multiple of these pores. And you see actually when you turn the structure in 3 dimensions that this structure is cubic. Okay, so you can easily see from this structure that it's really highly porous, because the pore walls really now are atomically thin. Okay, and because of that feature of metal organic frameworks, these metal organic frameworks have exceptionally high surface area, so that MOF5 has a surface area of approximately 2,900 square meters per gram. So it's actually several football fields of internal surface area here within 1 gram of material. So the discovery of these ultra-high surface areas in these morph materials has sparked a lot of interest in them. And meanwhile, virtually thousands of metal organic frameworks are known. And actually just switch back to the class. And one nice feature about metal organic frameworks is that one can actually tune the pore sizes with a greater predictability in comparison to other materials. So for example, zeolites are also pores, but they have thicker pore walls, they have smaller surface areas, and the pore structure is little predictable. Okay, but by the concept of so-called isoarticular chemistry, one can tune the pore sizes with a higher predictability. Okay, so for instance, here you have a metal organic framework which is called IR-MOF16, and it contains also zinc ions, but now the linker is larger in comparison to this one. We have 3 phenylene units instead of just 1. But the structure that this resulting morph makes is essentially the same as the structure of the morph5. It's just that now these clusters of zinc or 4 tetrahedra are further apart, and the respective pore sizes are larger. And using that concept of isoarticular chemistry, we can extend basically then also metal organic frameworks from the micropores pore regime to the mesopores pore regime. So here the pore is approximately 1.8 nanometers. This pore here is already significantly larger than 2 nanometers. So here we are really already in the mesopore range. So in contrast to other mesoporous materials like the mesopore silicas that we mentioned previously, these metal organic frameworks are fully crystalline. Okay, not only that the pores are periodically ordered, there's also crystallinity in the pore walls. Okay, therefore they have a greater structural precision in comparison to a periodic mesoporous silica, for example. Okay, so the first metal organic frameworks that were developed were mostly carboxylates, had carboxylate linkers, but there's also other linkers that can be used. So one important class of metal organic frameworks are the so-called zeolitic imidazolate frameworks. So in this case, you use an imidazolate anion as your linker. Okay, and in a certain sense, there's an analogy between an imidazolate linker and an oxo linker in zeolite chemistry. Okay, so I've told you previously when we discussed zeolites, and in zeolites we have an average 145-degree bond angle between the O2- ion and the silicon 4+ ions which are tetrahedrally coordinated. And now the zeolitic imidazolate analog has now imidazolate anion, which has only one minus charge, okay? But the two nitrogen donor atoms, okay, also produce an approximately 145 bond angle between them and the metal cation, whereby the metal cations are then M2 plus um, uh, cations in order to produce a neutral framework. Okay, so here in the case of the zeolites, we need silicon 4 plus in order to charge compensate the O2 minus. Here we only need M2 plus in order to charge compensate the imidazolate anion, which only has a 1 minus charge. Okay. So now again, you have a great variability of chemistry. For the chemistry here, again, you can use many metal cations that have a 2 plus charge. You can also use, well, imidazole linkers that have different substituents. So in 2010, that was 10 years ago, there were already 90 CIF structures. I'm sure there are many more, I guess multiple hundreds, if not thousands today. So they have some advantages over the carboxylate-based framework. So they tend to be more stable. So, for example, the MOR5 and all the IR-MOF16 that I previously talked about is chemically not particularly stable. It's thermally fairly stable up to 400 degrees Celsius, but it's chemically not particularly stable. So if we let these materials just sit in air, then in the presence of moisture, water can actually replace the carboxylate anions as coordination sites. And that means that your metal organic framework essentially hydrolyzes. And then the structure is gone, the structure collapses. So with the imidazolate framework, this is not so much a problem. They tend to be more stable under ambient conditions or even in aqueous solution. Having that said, it's actually also possible to make carboxylate-based metal organic frameworks that have a high chemical stability if you use cations that have a very high positive charge. Zirconium 4 plus, for instance, is known to produce quite chemically stable metal organic frameworks with carboxylate anions because of the very strong electrostatic interactions between the zirconium 2 plus and the ligand. So this bond does not hydrolyze easily anymore. All right, so just for illustration purposes, I also wanted to show you here in 3D how such a ZIF actually can look like. Let's go here to ZIF metal organic framework. I have to go back to share this. Okay, so this one is called ZIF 8. Just zoom this out here a little bit. Okay. And you see here again that we have a highly paused structure in which now imidazole links actually zinc 2 plus cations. All right. So these structures, ZIF structures, are actually the structures with the most complex unit cells of all porous materials known. You see actually here the two record holders. That's the ZIF 95 and that is the ZIF 100. And they both contain this linker here, which is a modified imidazole. It's actually dichlorinated benz imidazole as a linker. And just under slightly different reaction conditions, they form two highly complex metal organic frameworks with zinc. Okay, so this one here makes a giant cage that measures approximately 3 times 2 nanometers and comprises 1,648 atoms. And these are 80 zinc atoms, 784 carbon atoms, 448 hydrogen atoms, 224 nitrogen atoms, and 112 chlorine atoms. So this cage here that makes up the structure of ZIF 100 is even larger. It actually has, the cage has 264 vertices, and its outer diameter is 6.7 nanometers, and its inner diameter is 3.5 nanometers. So it's made of overall 7,524 atoms. Okay, 664 zinc, 3,604 carbons, 2,085 hydrogens, 26 oxygens. That can't be right. There must be a typo here. That is certainly too little. Maybe it's not, because oxygen in theory should not even be in there. That must be from water coordinated somewhere. 1,030 nitrogen atoms and 515 chlorine atoms. So the unit size associated with these ZIFs is also then extremely large. Okay, and the crystallography of these ZIF structures is highly non-trivial, just because you have to localize so many different atoms within the unit cell. We've previously talked about crystallography before, how we can actually find the atoms within a unit cell. And basically, the more atoms there are in the unit cell, the more complex your crystallographic task becomes. So structures like this are crystallographically very demanding due to the high number of atoms within the unit cell. So here's just another size comparison. So you see here the Buckminster fullerene C60, which is a diameter of 10.5 angstroms. Here, this is the cage of the large pore feuersite structure, the FIAU framework type. So you see here, ZIF 95 already dwarfs that with a diameter of 4.1 nanometer, and even larger is than ZIF 100 with an outer diameter of 6.72 nanometers. Okay, then these already large cases are arranged into even larger, well, unit cells containing multiple of these cages that can be interconnected, that are interconnected by smaller cages. So you see this, how this is being realized for ZIF 95 and ZIF 100 respectively. So you see here the 8 cages that we previously considered, and you see that they're interconnected by smaller cages now. These are the blue ones here, and these are the green ones here. They're even very small cubic cages in the center. Okay, and similarly here on that side, you see the 8 cages, the largest ones that we previously considered. And they are also packed in a specific way and interconnected via We have smaller cages producing the overall unit cell. All right, these are fascinating objects of solid state chemistry due to their extreme complexity. Okay, but on the other hand, also still they're extremely high order. All right, so now let us move over from metal organic frameworks to what is called covalent organic frameworks. So metal organic frameworks are relatively easy to synthesize because they have dative bonds in between them. You can synthesize them relatively easily in a solid thermal synthesis using a relatively high boiling point solvent such as DMF from metal nitrates and the respective organic ligand. And because of the dative nature between the metal and the ligand, there's a fairly high degree of bond lability. And that because of that high bond lability, you can achieve crystallization fairly easily at fairly mild synthesis conditions. Okay, so you only need to heat your reaction mixes typically to temperatures of 80 to 100 degrees or even slightly above. Okay, so now when we have regular covalent bonds, which are not really dative in nature, then these covalent bonds are significantly more inert. Okay, so they cannot get cleaved and reconstructed at a high rate. Okay, and therefore it is much more difficult to produce crystalline porous frameworks that are interconnected by regular covalent bond, or at least it was believed so until the first crystalline covalent organic frameworks were discovered in the year 2005. Okay, and in these frameworks we have again either crystalline microporous or crystalline mesoporous materials, but we are not having metals involved anymore, only organic components and other non-metal elements. So for instance, boron. So the first covalent organic frameworks were actually boronic acid-based frameworks. So here's how this chemistry was conceived. So when you have a boronic acid like this phenylboronic acid, and you just heat it, okay, then water is getting eliminated, and you form the respective boroxine and hydride. Okay, that is here these three phenyl rings and this B3O ring, O3 three rings. Okay, and now you can extend this chemistry to make framework material. So this is certainly a molecule, not a framework, just by adding one boronic acid functionality to the phenyl ring. Okay, and do basically the same kind of chemistry. You heat this, and then water is getting eliminated. Okay, and self-polycondensation in the respective anhydride occurs. Okay, and now you can actually use the directionality of the covalent bonds in order to force this structure into a periodic structure. Okay, and with a high degree of certainty, you can predict what this porous structure will be, because the way how the covalent bonds are arranged allows you pretty much only one possibility. Okay, however, and that is very important, still the polycondensation that occurs here has to occur in a reversible manner in order to avoid the formation of kinetically controlled products. Okay. Imagine that, for instance, this carbon bond, which is a single bond, which is shown here, is actually allowed to freely rotate. Therefore, this group, for instance, at a particular point of time before it's actually fully condensed, or we can also look at this one here, can actually move out of plane. Okay, and once it's moved, and if it meets another molecule while it's out of plane, the two building units will connect incorrectly together. Okay, so if that bond formation was irreversible, we would probably arrive at a amorphous product, because the reaction would be kinetically controlled. That means that whatever forms first will be eventually also the final product. Okay, which is not necessarily the energy minimized structure. Only when the bond remains labile enough, then the system can actually self-repair, and it can self-repair itself into the thermodynamic minimum, which is then the crystalline structure shown here. Okay, which has these very periodic arrays of pores, which are 1.5 nanometers in diameter. So what now makes the bonds labile? Right? At first glance, you would say, well, the bond-oxygen bond is pretty strong, and the bond-carbon bond is also strong. But we have water here, which is getting eliminated from the reaction system as the polycondensation continues. Now, if you choose the reaction conditions right, you can actually decide or tune how much of that water remains in the reaction equilibrium. Okay, and that you can actually tune by choosing the relative volume of your liquid phase that contains the solvent and the reactants relative to the gaseous phase. Okay, so now using temperature, in addition, you can actually control how much of that water will actually be in the gaseous phase, okay, and how much of that water will actually remain in the solution. And that amount of water which remains in the solution can actually drive the chemical equilibrium to the opposite direction. Okay, the remaining water can actually attack here at the boron in the form of a nucleophilic attack and cleave the boron oxygen bonds. Okay, but only to a certain extent, so that the system can self-repair, not to an extent that would depolymerize the entire covalent organic framework structure back into the original reactant materials. Okay, so by this way of control, you can actually make a seemingly inert boron oxygen bond labile, and through that labilization, you can induce the crystallization of your covalent organic framework. All right, I see we are already over the time, so let us stop here.